We are going to take this Dorito burn data, and I'm going to show you a little bit of how to calculate the uncertainty in some data. This is something you'll have to do in an IB lab a lot. And there's 3 different types of calculation with uncertainty. You have, does anybody know? Have you ever heard of standard deviation?
Yeah.
Yes.
Okay. Like the most common.
I don't know if it's common, but you have standard deviation, and that looks like this. It's sigma equals, let's see if I can remember this.
Some of all the.
And then it's like x times minus factor of x squared all over minus 1, something like that. This is usually done in biology. Can they see me on there?
Yes, they can.
Yeah?
Yeah.
Should I turn it?
Maybe a tiny bit right. We don't see the whole board.
Okay. So this is usually used in biology. And that's, Mr. Richardson will show this to you. And this talks about this, you have to have a normal distribution for this. So you have to have data that kind of looks like that. It has to be created purely by chance. And that often happens in biology, so they use this. And then there's also smallest increment. Have you heard of this? The smallest increment is like if you're using a meter stick, what's the smallest space between the lines?
1 millimeter.
One millimeter usually. So if you said this is like 13.4 centimeters, you would say it's plus or minus 0.1, right? And then you just say, well, this is the smallest decimal place I have. So you just go plus or minus 0.1. You often get this in chem. So this is usually chem. And that's because in chemistry, you're working with masses and volumes and stuff that's really precise. And your instruments are pretty precise. And if you measure it 10 times, you're going to get the same number 10 times. And so then it comes down to this. But don't forget, that only works if you get the same measurement every time. And then you have uncertainty. And uncertainty is the max difference from the mean. What's the mean?
Average.
Good. This is the average as you know it. There's a few different types of averages, but we won't get into that. And this is usually what we use in physics. Because in physics, we are measuring stuff that's often, it's in the real world, and it's messy, like you found with your Dorito chips. Okay, let's go to this. Everybody got a copy made?
Yes, sir.
Okay. If you want to do this later and just watch the video, you can do that too. But so we're going to keep this kind of simple because I know you don't want to be here for too long. So this is what you're going to do first. Take this, highlight this last column, and let's make it thin like this. I've put in a few things that you need to know here, but we don't need them right away. We're going to compare this to the actual calories in a Dorito chip, and we'll see how close we got. The first thing we want to find, we have a final temp and an initial temp, right? So what would you calculate right away? Yeah, that's good, Nick. So let's do change in temp. And that's going to be in degrees Celsius. And what you do, have you guys ever done formulas in a spreadsheet? Yeah. Yeah? Who's made a formula in a spreadsheet? Okay, so a few of you. I'll try and make it big so you can see what's really big. anytime you start in a cell and you put equals, now you're gonna have a formula.
Oh yeah.
So I'm gonna say equals, and I'm gonna click on my final temp, and I'm gonna say minus my initial temp. And I'm gonna click go. And it tells me, oh, my difference is 9. Okay.
Only ours are all.
So, and then if we want to do all of these, oh, by the way, is Jamie or Jake here? Hey, Jamie, did you have a final temp? 28? Nice job. Okay, good. I'll put that. If you copy this, so you say Control C, and you'll see it gets highlighted. And then if you highlight the rest, so if you press Shift and highlight that column, and then how do you copy? I mean, how do you paste?
Control V.
Control V. So hit Control V, and that'll paste down all your formulas.
That's great.
So that's our change in temperature. Okay, are they all the same number?
No.
No, they're not even close, right? So there's a lot of uncertainty in these numbers. How would you, if you wanted to say in a lab report, if you had done this all yourself and you had burned 6 Doritos and you wanted to say, you wanted to give an idea of the change in temperature from burning a Dorito, how would you deal with these numbers?
You could average them out.
Yeah, we're gonna average them out. So let's do that. Let's go down here and just underneath we'll write average. And then we're gonna say equals average, because we don't wanna do the whole calculator thing, right? So you just type in average, you put your brackets in, and it's actually like highlighting them for me. So if you just wanna press tab, you can do it a bit of the cheater way. Or you can highlight these all, and then you can close the bracket and press equal, and that's gonna give us an average.
Actually, we got
7.8
7.
or so?
No, I got 7.
You got 7?
Because I think on mine there's also my calculation.
Oh, okay. Well, that's fine. This has a whole bunch of decimals on it, right?
Yeah.
So you can go up here and click one of these, and you can make that a little bit more easier to look at and say, oh, this is 7.8. Okay. That's my average. So look at those numbers. If you were to tell somebody, yeah, if you burn a Dorito, you're gonna get 7.8 degrees Celsius change. Is that true?
No.
Kind of, right? Nick says depends, yeah.
Can be.
On the size and oiliness.
Ah.
Data.
Oh, so there's that's good, Uni. So one source of uncertainty for us is the
It's
size of your
variable.
Dorito. It's a variable, right? That's right. So this tells us something about it, but it doesn't tell us how much up or down we might expect to have, right? And that's where the uncertainty comes in. So it's not like life or death that we know the uncertainty of burning a Dorito, but sometimes it is life or death to know, for example, how much a steel beam will deflect or how much a bridge deck will expand. That sometimes there is lives depending on that uncertainty rate, right? And so this is how we do this. So we take that average and we say, well, let's find the difference between all of our data points and that average. So we're going to do another formula. Press equals, and you're going to highlight your first data point and press minus, and then click on your average and hit enter. And then for now, just copy it down. So you can, if you want to copy it down, the easy way is you grab this little box, this little block at the bottom, and you can just drag it down and you copy it. Is this right? Those numbers right? No. This number didn't even change, right? None of them changed after that. Why? Because we just copy and paste. So if you look at this one, if you highlight the formula, it's grabbed the right data point, but it's not subtracting the average anymore, it's subtracting the box underneath it. But we want all these ones to be the difference between that data point and the average. So the way you fix that is you go back to the top box, and instead of just, if you highlight this, and your average is kind of faded out there, we don't want that number to change when we copy all our formulas down. Yeah. Somebody's having fun out there. We use dollar signs. If you put a dollar sign before the letter and after the letter of the cell, then if you copy that formula now, it'll always keep that G20. For me, it's G20. I don't know what it is for you guys. So you hit enter, and then you copy that one down. And now you should see, okay, now I got the right numbers, because 11 minus 7.8 is 3.2, da 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 da. Is that making sense so far?
Yes.
Okay, good. Some of these numbers are negative. And we don't really want the negatives in there, it's kind of messy. So we're gonna add something again to our formula. Go back to the top one. Do you guys know what it's called when no matter what, the number comes out positive? Very good, thank you. What was your name? Miles. Very good, Miles. The math way of doing this is absolute value. So just type in ABS and then put your cells in brackets. And if you click that and highlight those, it will give you a number, and I'm going to back these off because that's just a few too many decimal places for my liking. And you'll notice these are all positive now. Okay, we're almost there. So that's my difference. It's the difference between all my data points and the average of those data points. We want the biggest difference, because we know that if we have a bunch of data points, the right value is probably within this range. Okay. So we want to find the maximum. So type in max, and underneath that go equals max. And you make your bracket, open bracket, and then you highlight all these data points. And that'll find you the maximum. Now, you might be thinking, well, couldn't we have just looked at it and seen that this is the biggest one? And the answer is yes, of course, you can. But when you're in IB, and if you might become an engineer or you're doing some software architecture or something, you might have 1,000 points of data or 10,000 points of data. And it's too much trouble to look through them all. So we let our computer do that and find our maximum. Okay.
Wait, how do you do it?
Charles, say that again.
I was asking how do you do it?
How do you find the max? You type in equals, and then just type out max. And then you put brackets and highlight your differences. Okay. So what do we do with this? If you want to say, what's the temperature increase for a Dorito, burning a Dorito? We would say that our change in temperature, I might say delta T, is equal to 7.8 degrees plus or minus 3.2. I would say degrees Celsius. And that's how I would write this in an IB lab or in a research paper or something like that. Now that's a lot of uncertainty, right? Because our lab was messy and we had all kinds of sources of error and all kinds of, and I wanted that because I wanted to show you. If you said, well, hey, our thermometer is within 1 degree, and if you just took the smallest increment and said, no, it's 7.8 plus or minus 0.1, because that's my smallest decimal point, would that be correct? No, how do you know it's not correct?
Because there's other values that are out of that range.
Exactly, Nick. Good job. So these differences are way bigger than 0.1, right? So if your plus or minus is 0.1, you should never measure anything greater than that or less than that. So this kind of tells us, yeah, we're pretty sure it's within that range. Okay, and that's how we do uncertainties in physics. Two types of error. When you, can I turn this off now? This will all be on the video so you can watch it later if you need to. When you write an IB lab paper, I know you don't need that right now, but there will come a day when you really need it. And you're going to write about sources of error. Error is not a mistake. Okay? Error is the inherent uncertainty in a measurement. And there's two types. There is random error. Random error is what we just calculated. And so, as Uni said, there's different sizes of a chip, and maybe you had a little bit different water level, and maybe you had your Bunsen burner was a little different or whatever. Maybe you burned it, you lit it, and you held it a little bit longer than somebody else before you put it under the beaker or whatever. That's all random error. Pushes some of the data points up and some of them down. So that's this. Also have systematic error. Knowing the difference between these two and being able to think about sources of these is really important in IB. Does anybody know what systematic error is? Always what?
If you do the same experiment.
Yes?
Same, like maybe with like different random errors and stuff, that one error always stays the same. Or something like that.
It's a good guess. It's a good guess. You're kind of on the right track. A systematic error is something that pushes all the data in one direction. So I'll write that down. So, if you look up how much, you have to do some calculations and stuff. If you look up how much temperature change there should be, like how much the water should be heated, it's more than this. Why do you think our water did not heat up as much as it should have? Ryan?
Inaccuracies.
Okay. What kind?
Maybe like
Arsha?
Like some of the heat went to the air, the glass, the steel and stuff.
Right. So if you want to measure all the energy in a Dorito, really you should be doing it in a sealed container, right? We should measure the change in temperature of everything around that Dorito. So as Arsha says, we're burning it out, and some of the heat's going into the metal and some of it's going into the air, and we're trying to heat through a glass beaker, which is an insulator, so that has trouble and everything. All of those sources of error are systematic errors. It's not a mistake. It's not a terrible thing. It's just something you have to be aware of and you have to define it. That's it. Do you think if you watch this video, you'll be able to